Good day, everyone. This is Mr. Couple, and this is PHYZR number 2, Taking Measurements. This is from the Prelims chapter, and it's page number 2. Please take a moment to set up your notebook paper. Remember, the title goes at the top of the page, and the chapter and the page number goes at the bottom. Today's lesson is all about taking measurements. Measurements are the most fundamental aspect of physics. When we do physics, we take measurements. For example, in our last lesson, we talked about the distance it takes for a car to stop and how it depends on the speed of the car. If we want to figure out the relationship between the speed of a car and the distance it takes to stop, we have to begin by taking measurements. So all of physics begins with taking measurements. And today's lesson is all about measurements. When taking measurements, there are two vocabulary words that we need to understand. The first is a physical quantity. A physical quantity is any characteristic of an object that can be measured. So we're not talking here about objects that can be measured. We're talking about characteristics of objects that can be measured. So for example, if you think about a pencil, an object, what are some characteristics of a pencil that could be measured? Maybe you're thinking we can measure the length of the pencil. Here are some other physical quantities we could also measure. We can measure the speed of a pencil. We can measure the temperature of a pencil. We can measure the weight of a pencil. And we could also measure the time it takes the pencil to complete some event. Perhaps you could throw the pencil into the air and measure the amount of time it takes for the pencil to fall back to the ground. Maybe you can measure the time it takes to snap a pencil in half. All of these are physical quantities. These are characteristics that can be measured. And in physics, these are the quantities that we want to know how they relate to one another. We want to know their interrelationships. In our last lesson, with the example of the car, we figured out how the speed affects the length that it takes the car to stop. So that's the goal of physics, is to figure out the interrelationships between all the different physical quantities. And if we want to determine these relationships, we have to measure the physical quantity. Now, how do you measure the length of a pencil? How do you measure the speed of a pencil? Well, in order to measure, you need to have an instrument. And every instrument will have some indications, some markings, or some readout. And it will always present the measurement in terms of a unit. So a unit of measure is a standard used to measure a physical quantity. So for example, if we want to measure length, we can measure the number of inches. And that number of inches would give us a measurement of the length. If you want to measure speed, you could use miles per hour. Temperature could be used in Celsius. Weight, we could use pounds. And for time, we could use seconds. These are units of measure. These are the standards that are used to make a measurement of the physical quantity. You have to be careful. Many students confuse units and physical quantities. It's extremely important that you do not confuse these two ideas. The reason it's important not to confuse physical quantities and units is because they both have very different uses. Formulas in physics are always written in terms of physical quantities. If you see the formula F equals ma, these symbols do not represent units. They represent physical quantities. In this formula, F represents force, m represents mass, and a represents acceleration. These are physical quantities. These are characteristics that can be measured. And measurements are always written in terms of units. So here we see F equals to 10. We know that the F is not a unit because it's not a measurement. The measurement is 10, but how do we show that this is a measurement? And the way we show that is by, after the 10, placing a unit. So if you ever see a symbol or some letters that follow a number, you will always know that those symbols are a unit. So the pounds is a unit because it follows the number Together, this makes up the measurement. The F over here on the other side of the equal sign is a physical quantity. And we know that because it's all alone by itself. There's no number in front of it. You can imagine if I had 10F, now the F would no longer mean force, it would mean farads, which is a unit that measures capacitance. So depending upon where a letter or a symbol is placed and how it's used, it can have a completely different meaning. So you have to understand the difference between a unit of measure and a physical quantity. Here are 3 instruments that are used to take measurements. The first one on the left is a ruler. This one in the middle is a stopwatch, and the one on the right-hand side is a scale. I'd like you to take a moment and think to yourself, what physical quantity do these instruments measure? So one more time, that's what physical quantity do these instruments measure? What I'm doing right now is checking to make sure you understand the difference between a physical quantity and a unit. The question I asked you was, what physical quantities do these instruments measure? So the ruler, the first one on the left-hand side, those tick marks are the units. So on this ruler, those are centimeters. But that's not what the ruler is measuring. What a ruler actually measures is it measures distance. That's the physical quantity that's being measured. So hopefully you thought distance for the ruler. Or maybe you said length or height. Those are all physical quantities. However, you should not have said inches or centimeters. Those are not physical quantities, but rather those are units. Now for the stopwatch, you can see the little tick marks. Those are seconds. But seconds are not what a stopwatch measures. A stopwatch measures time. The physical quantity is time, and the seconds are the units that the stopwatch uses to measure how much time has passed. And lastly, the scale. Scale measures weight. Those lines and those marks in there are pounds. Those are not what a scale measures. A scale does not measure pounds. It measures weight, and it uses pounds as the unit to measure the weight. Now let's think about what I want right now, actually, is I want you to have 3 columns on your page. So 1 column for distance, 1 column for time, and 1 column for weight. And what I'm going to ask you to do now is to take a moment and I want you to write down as many units as you can think of for each physical quantity. So how many units can you think of to measure distance? I'll give you one to start with. We could say inch. How many units can you think of for time? I'll give you one to start with. We'll put seconds. And then how many units can you think of for weight? I'll give you one to start with, and that's pounds. So what I want you to do right now in your paper is write down as many distance units you can think of. You're going to write them all right here. How many can you think of? How many ways to measure distance? And over here, for time, how many units can you think of to measure time? And then finally, how many units can you think of to measure weight? I'll give you a few moments to complete this chart. If you're having trouble coming up with some units, you can think something like, for distance, you could ask yourself a question like, how tall am I? And think, what units are you going to be using when you say how tall you are? Or maybe for time, you could say, how old am I? What units would you say for how old are you? What would you say to that? What units? Or maybe for weight, you can think, how much does a car weigh? Or how much does an elephant weigh? So you could ask yourself questions, because realize that every day of your life you've used units. You've been using them since you're a little kid. You understand the different units. And now I just want you to make a list of how many units you can think of. I want you to fill this table up with as many units as you can think of. I'm going to fill out some units on this table, and if you put these down, great. If you didn't put these down, you might want to add them to your list. So let's go ahead and I'll just throw in some distances here. Feet, meters, miles, light years. If you don't know what light year is, actually a lot of people get confused and they think light year, isn't year a time? Why are we putting this under a distance? Well, a light year is actually a distance. It's a measurement of the distance that light travels in a year. It's a very, very, very long distance. So a light year is an extremely long distance. Let's move on to time. Here are some units of time. Year, minute, day, week. Now, those aren't the only units. I'm just giving you a few units just to check on if you got the hang of this or not. And for weight, here are some for weight: tons, ounces, stones, newtons. A lot of people ask me, what's a stone? What the heck? Well, stone is 14 pounds. And a newton, maybe you've never heard of that before. A newton is what we use as scientists. This is the metric unit to measure weight. It's named after Isaac Newton. Now, I'd like you to take a look at your list for weight because I'm sure that there's a few that you think I've missed. What about grams and kilograms? What about liters or gallons? Well, it turns out that those are not weights. See, weight is a force. These are units of force. Weight is the force of gravity. If you put grams, grams actually measure mass. So you would not put grams to measure weight. Now, a lot of times we use grams or kilograms when we weigh things, but that's sort of a mistake. We should actually be using newtons when we make measurements of weight. We'll talk more about the distinction between mass and weight in a future lesson, a couple of units from now. Anyway, if you put grams on your list, please cross those out. Those are not correct. Don't erase them, just cross them out. And also, if you put liters or gallons, those are measuring volume, which is the amount of space an object occupies. Those are not weights. Weight, mass, and volume are things that students usually confuse. It's okay if you made that mistake. Make sure you learn from the mistake and cross out any instances of grams, gallons, liters that you may have put down in this column. Now that we've got this full completed list, I have a discussion question for you. Remember, we know it's a discussion question because it's in green. So that means you're either going to discuss it with someone who's watching this video with you, or you're going to discuss it with yourself. The question is, why are there so many different units? Why can't we just have one unit for each physical quantity? Why do we have so many different units? Can you think of any good reasons why there are so many different units? Well, the reason we have so many different units, and maybe you thought about this or talked about this, the reason we have so many different units is because there are many different sized objects in the universe. And we need lots of units because physical quantities come in many different sizes. For example, you wouldn't want to use inches to measure the distance from the Earth to the Sun. It doesn't mean you can't use inches to do that. You just wouldn't want to do it. It's much easier to use, for instance, miles. You just say it's 93 million miles. If I were to say how many inches it is, it would be such a large number that I'd have difficulty saying it. Likewise, you wouldn't want to use ounces to measure how much a person weighs. Be like, oh, I weigh this many ounces. What? I weigh 2,000 million ounces? What are you talking about? It's much easier to say I weigh 150 pounds. So we need different size units because there are different sized objects that we're measuring. I'll give you some examples. So you could say, last night I slept for 28,800 seconds. And it's true, that's how long I slept last night. I could also have told you last night I slept for 0.0009 years. And these would be the same exact measurement. These are the same. That's how long I slept last night. I slept for 480 minutes. I slept for 0.33 days, which means I slept for 8 hours. Now, what's the best unit to use to measure the amount of time that you slept for last night? From this list, which one would you pick? I think you'll agree with me that the one that makes the most sense, the easiest to understand, is 8 hours. And last night I slept for 8 hours. So the unit hour, the size of that unit, the amount of time represented in an hour, matches how long I slept for last night the best. So that's why I'd want to use it. Now, if I took a nap, maybe it would be better to use minutes. Like I took a nap for 40 minutes. So you want to make sure that the unit that you're using fits what you're measuring. Here's another example. The length of my pencil is 76,200 microns, 0.00005 miles. I had trouble saying that one. 76.2 millimeters, 0.25 feet, 3 inches. Keep in mind, all of these measurements are the same measurement. They're all the measurement of this pencil, but they all look completely different because they're using different units. Which one would be the best to use to measure the length of the pencil? I'm sure you'll agree with me. 3 inches would be the best measurement. Yeah, my pencil's a little short. It kind of got broken. What if we wanted to weigh a person? Which unit would be the best to weigh a person? Yeah, see, he was already telling us the answer. He was pointing right at it. Pounds. Pounds would be the best to use to measure a person. What about measuring the distance from Los Angeles to Las Vegas? We're in Los Angeles, so what if you wanted to say how far away Las Vegas was? Which unit would be best to use? You wouldn't want to use light years, because light year is way too long. You wouldn't want to use inches, because inches are way too small. The best unit to use would be miles. It fits the distance the best. How about if you wanted to give your age? Of course, we'd use years. You wouldn't say, I'm a billion. And it turns out that I actually am. Well, I'm a little bit over a billion, but last year I was actually a billion. I celebrated my billionth birth second last year. I was a billion seconds old. That's kind of weird, right? You'd rather say, I am 17 years old. I am 32 years old. It makes way more sense to use years. Something that we can all relate to. And to weigh a car, we would use the best unit to use, tons. You can make a case for saying pounds. Oh, my car is like 6,000 pounds, but it's much easier to say my car is 3 tons. The question is, how long is a lab table? Now, if you were in class right now, when we did this lesson in class, all students are sitting at a lab table, and I asked my students to actually measure the length of the lab table and then add it to the list. So unless you're sitting at a lab table right now, you can't really do this. So what we'll do is instead we'll look at what the students from my class, I believe it's from my 8th period, what they put for their measurements of their lab tables. So here are all the measurements that this class came up with for the length of their lab table. And just take a moment to look at these measurements. Something really interesting happened. Now, I didn't give them any rulers. I didn't give them any meter sticks. I just said measure the length of the table. And so you can see that every single group was measuring the exact same table, but they decided to measure it in very different ways. And this is the trouble with units. The trouble with units is that if we don't specify a standard or standard unit to use, we have no way of knowing who is correct. We have no way of comparing these to each other. So the question I asked students to think about was, which group measured the real length of the table? And I want you to think about that. All these students were measuring the exact identical table. They all sat at the same table. But they all have completely different measurements. So the question is, who measured the real length of the table? And I want you to think about that. there really is no correct answer to this question, because you can make the case that nobody measured the real length of the table. The real length of the table is an unobtainable measurement because you could never exactly perfectly measure the length of the table. You would have to zoom in down to the smallest size atom and try to measure that. And that's just not going to happen. So no one actually measured the real length of the table. You could also make the argument that everybody measured the real length of the table, that all of these units agree with each other. All of these measurements, that is, agree with each other. They've just used different units. So for example, you can actually see that there are two groups here that said folders, and they both got 5 folders. So that gives us a little bit of an idea that perhaps they both agree with each other, that both of these groups measured it correctly. There's even a group here that says 5 binders. Maybe the folders and the binders are the same object. Well, we don't know because these units are very general. We don't really understand. We don't know if they use the same folders or if they use the same binders. Likewise, for a group that uses pencils, does this mean that 10 pencils are equal to 5 folders? Now, I'm a little bit confused with that because here's another group that also used pencils, but they put 8 1/5 pencil. How could one group have 10 pencils and another group have 8 1/5 pencils? Does that mean that like they're all totally wrong? Or does that just mean that this group, the 8 1/5 pencil group, that their pencil is a different size than the group that said 10 pencils? So as you can see, this is a fairly complicated question. There's really no answer here. But the main thing to realize here is this. When we use different units, or rather I should say, when we don't all use the same units, it becomes very difficult to communicate. It becomes very difficult to make any sort of an analysis of the measurements. This is the trouble with units. We need to make sure that we all use the same units so that we can compare our measurements to each other and check for if we could verify different measurements with each other. So let's write this down. Having so many different units makes it difficult to communicate. So having two groups of scientists using two different types of units can lead to miscommunications. So if I want to know how long the table is, it's perfectly fine to say it's 10 pencils, and it's perfectly fine to say it's 5 folders. But how do we know that those are the same? Just by looking at them, how do we know that 10 pencils equals 5 folders? It's very, very, very difficult to know just by looking at those two measurements whether or not they're the same. It would be much easier if we said, okay, everyone, let's all use folders, and we'll all measure the length of our table using folders. And then it would be very obvious which groups measured the table correctly and which groups did not. They would just pop out at us. Because we'd see 5, 5, 5, 5, 5, 5, 5, 5, 5, and then we'd see a 6. Oh, what happened to that group that got a 6? Were they using the same folder? Did they make a mistake? So you can see that having many different units makes it very difficult to communicate. But remember, we needed many different units because of all the different sized objects there are. So now we're realizing that if we have all these units, it makes it very confusing. And what I'm going to do now is tell you a story about a horrible accident that happened because two groups of scientists and engineers were using two different types of units. This story is about the Mars Climate Orbiter. It was a spacecraft launched in December of 1998, and its goal was to orbit Mars and measure the planet's weather conditions. And so here you can see the rocket on the launch pad, and the rocket at the very tippy top is carrying the spacecraft. And we have liftoff. Now this video is a computer animation recreation of the launch. And I wanted to show this because of all the different intricate pieces that went into launching this spacecraft. Not only do we have all these rocket engines attached to this rocket and all these pieces, but there's also a coordinated sequence of events that must occur as the rocket launches up into space. Just look at all these moving pieces and look at all these parts. Here you can see the fuel tanks being ejected off the spacecraft because the fuel is empty. It no longer needs them, so it just lets them fall back down to the Earth. And you can see slowly, piece by piece, the rocket starts to fall apart as the pieces are used up and it no longer needs them. Look at all the orchestration that goes into this, all the planning, all the calculations that are involved. Imagine how difficult it is to do this. Well, I shouldn't say difficult, but I should say challenging. Imagine how complicated this is. Then a spacecraft fires its thrusters to take it on a course to Mars. Here you can see the smaller rocket engines spinning up the spacecraft. And it'll actually use this rotational inertia on its flight to actually spin and orient the spacecraft in a desired direction. So it's getting up all this rotational inertia that it will use later on to steer the spacecraft. And now the spacecraft is just gliding, and since space is a vacuum, there's no particles of matter in space to slow the spacecraft down. There's no friction, there's no air resistance, and so the spacecraft will continue on its course and continue moving until it reaches its destination of Mars. Now the problem is if we don't act, if we don't intervene, the spacecraft is just going to go and fly right past Mars. So what we need to do is we need to actually slow the spacecraft down so that way it can insert into an orbit around Mars. And the way we do this is by firing reverse thrusters. So if the spacecraft is moving to the right, the thrusters need to fire in the same direction the spacecraft is moving. So if the thrusters fire to the right and it's moving to the right, the craft will slow down. And we want it to slow down so that it can enter into orbit around Mars. If the spacecraft doesn't slow down, it's just going to go right past Mars. So here's the Mars Climate Orbiter on its approach to Mars. You'll notice it's moving to the left. We're going to fire the thrusters to the left. Thrusters are firing, they're firing. And disaster, failure. The spacecraft slowed down way too much. It crashed into the atmosphere, burned up in the atmosphere of Mars, and $330 million were lost. So the Mars Climate Orbiter reached Mars. It burned up in the atmosphere. This is not what we wanted to happen. We wanted to orbit the planet, but the thrusters fired too strongly. The thrusters burned with way too much force, and the spacecraft slowed down way too much, and instead of orbiting around Mars, it actually crashed into the planet. So we slowed the craft down too much. It's a horrible disaster. $330 million were lost. The question is, why did this happen? What caused this accident? And it turns out that it's the silliest mistake ever. Think of all those pieces, all those parts, all the planning that went into this, all the years and millions of dollars it took to build this thing. And everything worked flawlessly. There was not a single mechanical error in this entire spacecraft. Everything worked perfectly. The problem was units. They used different units, and it caused the orbiter to crash. Now what happened was the Mars Climate Orbiter was a joint mission between NASA and the European Space Agency, ESA. So NASA designed the flight control software. So they're the ones who were they wrote the programs that would tell the machine how to function. So NASA designed a software that would tell the engines how to fire. And then the European Space Agency, they designed the actual engines themselves. And here's where the problem happened. So the problem is that NASA was using pounds for their unit of force, for the thrust on the spacecraft, whereas the Europeans were using newtons, which is the metric unit of force. And so when the flight controllers sent their signal to the engine to say, this is how much we need you to burn for the orbital insertion, they said 10 pounds. So they typed it in, boop, 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 and they said 10 pounds. So they sent that to the engines. Unfortunately, they didn't send the unit because the software wasn't designed to send the unit. It was only designed to send the number. So those 10 pounds, which were what NASA calculated that they needed to burn to get into orbit, they actually ended up sending 10 newtons. And the problem is that 10 newtons is 45.5 pounds. So 10 newtons is not equal to 10 pounds. In fact, 10 newtons is way more than 10 pounds. And this is why the engines fired too strongly. They fired about 4.5 times more strongly than they should have, which caused the spacecraft to slow down and then crash into the planet and burn up in the atmosphere. So the mission failed. The spacecraft mission failed because the two teams used different units. And that was it. There's no science mistakes. There are no engineering mistakes. Everything worked perfectly. The mistake was with their units. And that's the trouble with units, is that having these different units can lead to communication problems. And here's the perfect example of that. A $330 million mission fails because two groups of scientists and engineers use two different units. This is a completely avoidable mishap, and we should have known better. And I'm going to tell you now the story about why this is silly. So every 6 years, scientists from around the world meet in Paris to discuss scientific measurements. They've been doing this since the 1800s. And scientists have been meeting up in Paris and discussing how we should take measurements. What are the best techniques to use to take measurements? So in 1960, the scientists at this meeting created the International System of Units, which is also known as the metric system. So this is in 1960. They've created an internationally agreed upon system of units so that everyone in the world is standardized and using the same units. So here's NASA sending a spacecraft to Mars in 1999 that crashes because they used different units when this problem had already been resolved in 1960 with the metric system that we would all use the same units for our measurements. That's why it's such a silly mistake. We should have all been using the metric unit. Now, since they're meeting in Paris, they actually didn't call it the International System of Units. They actually wrote it in French. And here you can see a picture of the front of the booklet that they published. And it says, Le Système International d'Unités. I don't speak French, so that was my best attempt at it. Notice that it says SI. That stands for the Système International. Well, in English, we call that the International System. So whenever you see SI, it just means that it's the International System unit. It's the agreed upon unit that everyone in the world has agreed to use. So the way the metric system works is it assigns one standard unit to each physical quantity. So for example, for time, we're supposed to use seconds. For weight or force, we're supposed to use newtons. So that's what the metric system says, that every single physical quantity is assigned one standard unit. So a standard unit is the one unit that all scientists have agreed to use. That's why it's called a standard unit. This is the International System Unit, also known as the SI unit. Now, every country in the world has adopted the metric system, except for 3 countries. And these countries are shown in gray on this map. The 3 countries are the United States of America, Liberia, and Burma, also known as Myanmar. So every country in the world has agreed for all government purposes to use the metric system except for these 3 countries. Now, there was a movement to introduce the metric system into the United States, but it was met with a lot of resistance, and they only implemented it partway. They had these plans to roll it out in phases, and the first phase was to start it on bottles for fluids. So that's why when you go to the grocery store and you buy a bottle of soda, it says 2 liters. Liter is the metric unit for volume. So we actually started to phase in this metric system conversion, but it was met with a lot of opposition, and people did not like it, and so we stuck with our imperial system of units where we measure distances in miles. So all the road signs you see, it says, 270 miles or speed limit 65 miles per hour. So the United States of America does not use the metric system. We're one of the only countries in the world who does not use it. So here's a question for you to think about. What do you think the standard unit is for length in the metric system? What is the standard unit for measuring length? If you said the foot, you're wrong. If you said inch, nope. If you said miles, nope. The standard unit of length in the metric system, the SI unit, is the meter. It's abbreviated with a lowercase m. See, the United States doesn't use the metric system. When I say meter, Most people, most students are like, huh? What the heck's a meter? So I thought it'd be fun to give the height of a few NBA players in meters. Here's the shortest player in the NBA right now. His name is Earl Boykins. And he's standing next to Shaquille O'Neal, who is one of the taller players in the NBA back when he played. I thought this was a funny picture. So here are their heights from the point where their feet touch the ground up to the tippy top of their head. Now, Earl Boykins is 1.65 meters, if we give his height in meters. It's a little weird to say meters, isn't it, for people that aren't used to the metric system. And Shaquille O'Neal's height is 2.16 meters. Now, I guess I should be friendly here and say that 1 meter is 3.28 feet. So see, when I give you the unit conversion, you can actually see, oh, okay, so 2.16 meters. So if I wanted to figure out how tall Shaquille O'Neal was in feet, I would have to take 2.16 meters and multiply that by 3.28 feet, and then I could convert it over to feet. But see, we don't want to do that. We don't want to have to deal with these unit conversions. We don't want to use multiple units to measure things. We want to use the same unit. So from now on, in this class, we will always use meters when we measure length. We will no longer use feet. We will never use inches. We will never use miles. We will always use meters. The problem with using one unit to measure all the lengths of all the objects in the universe is, like we said earlier, there are different sized objects. So how long do you think, or what's the length across the nucleus of an atom? So we're talking about from one end of the atom to the other end of the atom. How many meters is it? Well, this is how many meters it is. Notice how small that number is. This is so confusing. I thought we were trying to use the same unit to make things less confusing, and here we have this crazy small number. It doesn't get any better. So here's the influenza virus. The length of an influenza virus is this many meters. I'm not even going to bother trying to say it. There's so many zeros up there. It's such a small number. I'm just going to show it to you. The width of a human hair. The length of an ant. The length of a human. Average human is about 1.5 meters. This is a picture of me and my wife standing at the Grand Canyon. Oh, this was taken so long ago when we were skinny. I'm not that skinny anymore. Downtown Los Angeles, the city we all love and where we live. 10,000 meters. Hey, I could actually say that one. 10,000 meters. So from one end of downtown LA to the other end of downtown LA. 10,000 meters across. Let's get larger, from one end of the Earth to the other end of the Earth. About 10 million meters. From one end of the sun to the other end of the sun. About 1 billion meters. From one end of the solar system to the other end of the solar system. 10 trillion meters. Oh, this is very quickly going to start to get to where I can't say these numbers anymore. From one end of the Milky Way galaxy to the other end. Well, a lot of students don't know what a galaxy is. Well, a galaxy is a collection of stars. Now, this is not actually the Milky Way galaxy, but it's our galaxy looks very similar to this one. So you can imagine if this were the Milky Way galaxy, where would the sun be? So the sun would be about 2/3 of the way out, and it would be a tiny, tiny, tiny little dot that you wouldn't even be able to see. Because there are so many stars in this galaxy. There are approximately 200 billion suns, 200 billion stars in this galaxy, that our sun is just a tiny little speck you can't even notice. Well, how long across is the galaxy? Gosh, should I try to say that? Let me see. Okay, let's try to say this. So, 1,000, million, billion, trillion, quadrillion, quintillion. So it's 100 quintillion meters. Oh my goodness. And you know what? Galaxies aren't the largest things in the universe. We actually have clusters of galaxies. We can have groups of galaxies. This is an image taken by the Hubble Space Telescope of literally thousands of galaxies. And you can see each one of these specks, each of these smudges, like this little speck here, or this speck here, each of these specks is a galaxy. And each galaxy is approximately 100 billion stars. So a group of galaxies is approximately this far across. I'm not even going to try to say that. Or we could look at the structure of the entire universe. This is a computer-generated image of what the universe looks like. Each of these specks are galaxies, and those, you can see like there's these bright spots, and those would be clusters of galaxies. So how far is it from one end of the universe to the other? This is approximately the size of the universe in meters. A ridiculously huge number. So we tried to come up with one unit. We didn't try to, we did. We came up with one unit, one standard unit that everyone would use to avoid confusion in our measurements. But that leads us to a pretty difficult problem, is that now all these crazy numbers, we get all these crazy numbers when we try to measure things using the same unit. We get these teeny tiny numbers when we're talking about atoms, and we get these huge numbers when we're talking about astronomical distances. So we need to fix this. And the way the metric system fixes this is it comes up with prefixes that we put in front of the unit to specify the size. So a human is about a meter. We can say that an ant is a millimeter for 1,000th of a meter. The human hair becomes a micrometer. Influenza virus is about a nanometer. And the atomic nucleus is about a femtometer. So we come up with these prefixes that can scale the size of the meter, smaller or larger, depending upon what we're measuring. So Los Angeles should be measured using kilometers. Kilo means 1,000. Earth can be measured using megameters, which means 1,000,000. The sun, we could use the gigameter, which is 1,000,000,000. And for the solar system, we could use a terameter, which is 1,000,000,000,000. Now, we make it even easier in this is we actually come up with an abbreviation, a one-letter abbreviation for each of these prefixes. So for meter, we just use M. So we could say a millimeter is mm, a micrometer is μm. If you've never seen this symbol before, it's a Greek letter mu. Say a nanometer is nm, and a femtometer is fm. We could also do that for the other ones. Kilometer is km, megameter is capital M, little m, gigameter is capital GM, and terameter is capital TM. We use capital letters for the large prefixes and lowercase letters for the small prefixes. And so now we've solved the problem. We're still using the same unit of measure, the meter, and we just scale it up or down using these prefixes. So now there's no confusion. We're still using the meter. And there's also no confusion because we just put these prefixes to scale up or scale down the meter. And this is how the metric system works. And this is why the metric system is so awesome. And next class, next time I see you guys, we're going to be doing this in more detail. I'll have a handout for you, and that'll be page 3. And that's what we're going to do next time. Until then, have a wonderful day. I'll see you in class.